Good day everyone and welcome back to the class. So there are a few important topics that I want to re-emphasize or rather go more in detail before we move on to the numericals, okay? Because I understand there weren't things that were fully clear last class. So we'll go more in detail now and probably a bit more slowly. So firstly, you have heard this word a lot, right? Policy iteration and value iteration, okay? Now what exactly is policy and value iteration? Policy iteration, so there are two ways you can improve the policy, okay? One is policy iteration, the other is value iteration, okay? Policy iteration is a two-step process. Value iteration is a one-step process, okay? That is, this involves policy evaluation and policy improvement. This combines these two into one step, okay? You've evaluation and improvement in the same step. Now what is policy evaluation? In policy evaluation, what you do is you start with a random policy, okay? By random policy, okay, what is policy basically? What is a policy? Set of actions, right? Policy in general is a set of actions, okay? Now here, we start by random policy. What I mean here is you can take any actions, okay? You randomly fill this matrix or this vector with random actions. It can be anything. At that point in time, you do not have any knowledge of the policy or how good or bad it is, okay? So you just define actions A1, A2, A3, A4, A5 and so on, right? This is your initial random policy. Now when you have a policy, you need to understand how good or bad that is. How do you do that? Value function, right? The tool that the reinforcement learning provides you to evaluate a policy are value functions. Two value functions, state value function and action value function, right? State value function, it implies it is function of only one entity, and that one entity is a state. The action value function, on the other hand, is a function of two entities, state and action, right? So in a given state, there are multiple actions that you can take. However, the state still remains one, right? So what the value function does is, it will choose the maximum value of the state, which is maximum of all the actions for a given Q value, right? However, Q value for one state can be multiple based on the actions. So you could have QSA1, QSA2 and so on. All right? Clear up until this point, right? Now, when you have evaluated this policy through this tool, which is your value function, you want to now improve it, okay? By improving, what you mean is, when you have the value function, you can get the Q values from that. How? You have Q is equal to a reward at this step plus discounted reward of the future steps, right? Your Q value. Your Q value is also dependent on V, right? So this you can get from your V, okay? When you do this, the action that gives you maximum value function or maximum reward in that state, or rather no, value function, would be the chosen action, which then replaces an action here, if it is better than the existing actions. Policy evaluation done, and then policy improvement. This together constitutes the policy iteration, right? Yes. Yes.
Where is the epsilon gradient here?
No, that's something for later. That is when we want to balance or rather improve the exploration. For now, we are not exploring anything. That will come later when we are studying about the Q learning probably, Q learning algorithm. So that is probably 2 or 3 steps ahead from now. Yes.
So you said evaluation and then
Improvement. Yes.
So the action quality function
Yes.
here is considered evaluation, right?
Yes.
Okay. And then
You improve based on that as well. So it helps you both evaluate and improve. I'll show that. Yes, okay. So, okay, is that the thing? Okay, yeah, I'll come to it. So now you're done with two steps, evaluation and improvement, all right? Now when you come to this one step thing, here what you are doing is you simply take VFS is max of all possible states and actions, the quality basically of that state action. This is done in one step, okay? Unlike here where you first evaluate V for all possible actions, here you do it all in one go and you select the maximum out of that, and then correspondingly your policy would be the argument max of Q of SA. Okay, what is max of A and argument max of A? They're not the same, by the way. Okay, here by max we mean we are selecting the maximum value of the Q function for all possible actions. Say you have 4 actions in one state, you list all 4 values here of the Q values basically, and then your V, corresponding V would be the maximum numerical value of this thing. Okay, now assume you have 4 states. Okay, say this is Q1, Q2, Q3, Q4. Okay, your Q3 is max, so now your V of S is basically Q3 numerically, right? Since this is at index 1, 2, 3, your argument max would be the third entity in the action space. Say your action space, like I said, has only 4, assume it is only 4 actions. So your maximum, your optimal policy would then be the third action. You get it? So your pi star in that state would be A3. Are we clear on this? Are we clear on this up until this point? Yes. It gives us the index of the maximum Q value, and then based on that index we select the action corresponding to that index, right? So this will give you the optimal policy. So we have V star, Q star, pi star, right? Okay, that is your policy iteration and value iteration. Okay, now again, when yes. Okay. Now that if you are doing it programmatically, it depends on your index. However, it is for now, because we are doing it by hand, it's simply 1, 2, 3, whatever, however you convention it, right? It necessarily need not be 0, 1, 2, 3 because you're not using the argument value as such. You're just calculating that particular index. You want that block. Okay? Okay. Now, for a given policy, how do you compute V pi? Yes?
Does that also have to be a scalar quantity?
Scalar quantity, you mean?
Just a value?
Yes, yes, yes. For a discrete system, because what is policy? Policy is basically all the actions, all the optimal actions threaded together, right? What it does is it will thread you all the optimal actions. So you already know the optimal states based on the value function, and whichever state you are in, you correspondingly you choose that action. You're like, okay, fine, this state, this is the optimal value. From that thread of actions, you select the optimal one. You get it?
Considering having a wave, does the policy can be have two actions in the same time by maybe the position and the weights of the wave?
Yes, for one, you mean, okay. For one state, you can have 2 optimal actions. Say for our grid problem that we were doing the other day, you have start at the top left and then goal at the right bottom. You can either go right and then go down, or you can directly go down and go straight. So that is what you mean?
No, the policy itself have two states can change to go for the optimal policy.
I didn't get it. What do you mean 2 states?
I mean two values.
2 values, okay.
Each one of them for physical probabilities.
In what sense? Can you explain it if you want on the board? Okay. Okay. So, okay. Now, when you are evaluating the policy, if you have a stochastic policy, your probability comes into play, right? In the sense, in that particular state, if you take one action, where will you end up? This probability determines that thing, okay? It determines where you will end up, given you take a certain action, okay? But you see this value function is summation over two quantities. Your probability, okay, given your for the next state, and another probability here, which is the probability of taking that action itself in that state. Like you're in state 1, okay, you have 4 actions that you can take. So this summation will sum the probability of taking all that actions. Now if it is equal probability, you will basically get for 4 actions 1 by 4, 1 by 4, 1 by 4. If it is 2, 1 by 2, 1 by 2, 1 by 2. This has to do with the transition of the states. So this is the probability of the state transition. This is the probability of selection of actions. So your value function will be a summation over these two quantities, starting from the innermost here, in the sense that first, for one's action, for one state, you select, if you take a given action, where will you end up? And then you sum it over all the possible actions that you can take in that state. Is that clear? You're in state, right? You can take 4 actions. But given you take any action, you can end up in 3 different states. So this probability will consider which all states you can end up in, whereas this probability considers the actions you can take in that state. Cool?
But solution automatically will give us 1.
No, this isn't a probable. Okay. Just this, if you just have this probable summation, then it will be 1. But here, mind you, are multiplying by some other quantity here. Yes, but then again, this summation is multiplied with this summation. So it will not give you 1 always. It is not a probability summation. Right? A probability summation will always result in 0 or, sorry, 1. But this one is not only a probability, it's probability multiplied by some other quantity, which isn't a probability. It is a value function. It can take any numeric value, not between 0 and 1. Right? Clear?
So this is expectation, right?
This is expectation. Yes, this is expectation. Yes, this is Bellman expectation equation. Okay. So yes, for a small MDP, you can solve it, if it is linear, you can solve it using the exact method, just by algebra. However, in most cases, when you use RL, probably all cases, dare I say, you will never have an exact MDP, you will never have a linear case, right? You will obviously have multiple states, multiple actions, a very non-linear MDP. So you will end up solving numerically, which is what we'll be doing. Okay, yeah. Like I said, so policy improvement is what? Your new policy would be the action corresponding to the maximum Q value. Right? Yes.
For the part of value iteration or policy iteration generally, does the process need to be an MDP?
Yes.
This is the first
Yes.
condition.
Yes. Yes. Yes.
If
Yes.
it's not, we can't use this recipe.
We can't. Yes. The entire concept of Bellman expectation equations or Bellman equations lies on the foundation that your MDP is a Markovian is fulfilling the Markovian property.
Okay. Sorry, another related question. Does a process, I mean, do we need to have a model to make sure the process is an MDP?
No.
Or it's not?
No. No. No.
It
No.
just need to.
It just needs to have
the
samples. Yes, state action samples. That's it. If you have enough number of trajectories, enough number of samples, you're good enough. Yes.
So over here, like policy, we do the quality function first, and then enumerate, and then get the argmax.
Yes. So first, this is the second step of policy iteration. The first step of policy iteration is policy evaluation, and that is done through the value function. because you basically need which states are good. And then when you're doing the improvement process, then you consider the Q function to generate a new policy, because the policy is action, and quality function, Q functions, are dependent on action. So that is why you have this, right? So first value function, and then the improvement state will be the max argument of the quality function, the Q function. Okay?
Sorry, one
Yes.
slide back.
Yes.
Over here you say got V or Q.
Because we can get Q pi from V pi. So if we have Q pi or V pi, we could still get Q pi from it through this equation. And then we can use Q pi for pi. These Q and V, we can obtain one from the other. There are,
The evaluation could be through one or the other.
yes, it could be, yes. But V pi is faster. That's why we use V pi. So to sum it up again here, for policy iteration, you fix a policy, start with a random policy, evaluate it, how good it is, and then improve it. Keep on doing this till the value functions stop changing over iterations, meaning that the policy is converged. Okay? Value function, however, it's only one step. You run the evaluation and improvement in one step, in the sense that you evaluate all possible actions in that state, you select the max out of it, and you repeat it till there is no change in the policy. Your policy is converged, meaning your agent has learned. Yes?
So if there's a local minimum or maximum, so my main question is, does MDP ensure that it's only one minimum or maximum?
Yes, Bellman optimality equations ensures that you will end up on a global minimum. So yes, that is solved inherently. Okay, now back to our favorite problem that we did, right? I will open the... So remember this transition and all those things, right? Let me start with this thing. Yeah, I want to make a few things clear now. We have okay. Okay, you can see this, right? Okay, yes. So in this problem, okay, the one that we'll be solving, we have deterministic transitions, implying if you take an action in a given state, you will always end up in a definitive next state. Deterministically, you can determine exactly where you will end up in. That part is one, okay, deterministic transitions. Done? The policy is stochastic, in sense that in one state you can take multiple actions, right? So is this part clear? Okay, and remember the summation that we had earlier, V is summation of policy times the summation of the probability times R plus gamma V S prime, V of S, right? This is for all S prime, this is for A. Okay, clear? Now this summation, just this summation is 1 in this case. Why in our problem? Why? It is deterministic, right? So this inner probability has to do with the transition itself, right? Because this is transition probability. So this would end up being like this, right? Clear? Clear? Okay. If you take an action, okay, yes. So remember we had two actions, right? 1 and 2. Okay? So here you will see the probability of taking action L in S1 is 0.5 because you can take two actions. The other action is taking right given you are in S1. You know the notations of probability, right? Like say you have P of S given A. This means this is a probability of S given A is already happening, right? This notation is given notation, right? You know that in probabilities. Okay. So yeah, again your action value function, you have this relation. Remember this relation as well, right? Q is equal to your instant reward plus gamma times or the discounted future value function. Okay. Also one more thing, let me make this clear here. Your value function for a given state, what is it? Okay, what is the value function? What's the formula for value function? V equals to R, which is the instant reward that you get for the transition plus discounted future value, right? So what does your value function assume? Your value function assumes there are two parts, right? There are two quantities here on the right side. One quantity assumes that you are making the transition, right? Then you will get this reward. What does the other part of this equation tell you? That you have a future, that you are going to do something and you will follow that value function, right? Implying if you are in a pre-terminal state, that is say in the grid world that we did, here is your goal and you are here, the value of this state is say +1, whereas the value of staying in goal itself is 0, right? So why does the agent not stay here simply? Because it is the value function 1 implies that you will take that transition which will give you the maximum reward, and it is the value for that point onwards. That is why you will have the highest value function just before the goal, okay? And because the value function assumes that you will go to the goal, only then will you get that reward, right? Clear everyone? Okay. Yes.
For that question, the summation, the other one, the second one.
Okay.
Okay. The summation is for the product pi times r plus so on, or the summation of pi itself and then the product.
No. This for 0.5 for one thing plus 0.5 for the other r plus this thing.
Okay.
Okay.
That's why it doesn't sum up to 1.
That's why it doesn't sum up to 1. Yes. Okay. Yeah, you can get Q recursively as well from Q, but we won't be using this often. That's why I'll not talk a lot about this equation so as to not confuse you people. Move on to the next one. Okay. Right. The next example that we have, which is more complicated, the grid one, that we'll do by MATLAB. This we'll do by hand. Okay? Yes.
The value of 1, the value of transition, not the value of this block. Is the value of the transition.
Reward, yes.
Transition,
Yes.
you can get the reward.
Yes, yes. Because value function is what? The sum of the reward of that transition plus the future value functions of the other states, or of the future rather, simply. I would recommend you all to do this with me. Okay. So, you're ready everyone? Okay. So your value function, you will have value for S3, value for S2, value for S1. Okay. Your value for S3 you know is 0 because it's given. your value for S2 would be what based on this equation? 1 by 2 times, sorry, yeah, what is your reward for one transition? It is minus 0.1, right? Minus 0.1 plus gamma is 0.9, 0.9 times, you will end up VS1, right? In one case. Yes, plus 1 by 2 times, your other reward function would be plus 1, right? Or is it minus 1 here? Oh yeah, okay, yes. Your transition is always okay, it is minus 1, not 0.1, okay? Plus 0.9 times VS3, which is 0, right? So you will get a certain value. For S1, again, if you take a left, you will stay in that state because it's an invalid move basically. So it would be minus 1 plus 0.9 times VS1 plus the other possibility is minus 1 plus 0.9 times VS2. Cool up until this point? Okay. Now we will solve this iteratively. Okay. When we are solving this iteratively, okay, let's keep this VS3 for now. Okay. When we are solving this iteratively, your initial V would be 0, 0, 0. Okay. Your initial value function, VS1, VS2, VS3. You have these equations here. In your first iteration, you plug in the values from here, your V1 or V0 rather, okay, into these equations. Then you get a next set of equations, right? You get V1. Please do it and tell me. Oh, I hope you can see it. No. Still do it. I want you to do it. What would your V1 be? That is your value iteration after the first sweep. Remember synchronous values? You have to always choose yes. Sorry? No, your value functions in this iteration would be? Yes, 0, 0, 0. Yes, not, yes. Correct? Okay. Correct? And VS3 would be 0. Right? Okay? This is your first iteration. Now in your next iteration, you will not plug zeros here. Rather, you would plug in what? Minus 1. Minus 1 here and minus 1 there. You repeat it. Okay? You keep on doing this for many iterations, then your converged value function would be minus 4.173 and minus 2.88 and 0. Okay? Now this step is called what? No, this step, what we are doing, this entire step, what is this? Evaluation. Right? This step is policy evaluation. Correct? Okay. Now what is the next step we have to do after this? Policy improvement. How do you do that? You take the Q functions now. So Q of S1 comma L, Q of S1 comma R for all the states and all possible actions. QS1, yes.
Last one is V what? V pi star?
V star, the optimal value function.
So if I have the optimal value function,
Oh yeah, okay, at this stage we still don't know, so let's just take it as V pi. Yeah, okay, yeah, because this is the first sweep, it is still not optimal, yes. Okay, so where were we? Okay, yes, so we did this. Now you have the optimal value you have the value functions now after the end of first iteration. What is your Q value function? It is R plus gamma times V if you take a left in S1, where will you end up? S1. So your value function will have to depend on S1. Whereas if you take a right, what would your value function be? Cool? So Q of S2 comma L, Q of S3 comma, sorry, S2 comma R, and Q of S3 comma L, Q of S3 comma R. Does it matter what you take here in S3? No, because it's a terminal state. Once you're there, you cannot take an action. That's it. It ends everything. It ends the game there. Okay? So this would be R plus gamma times, if you move left, you're going to VS1. If you take a right, you're moving to VS3. Here it is simply 0, 0. Cool? Okay. Now you have your value functions, the converged value function. You plug that values here. Right? When you do that, you get some values here, minus 4.76, minus 3.59, minus 4.76, minus 1, this is 0 and this is 0. Okay? Now this are grouped together, this are grouped together. Why?
It is the same state.
Same state. So your value in this one, okay, now comes your improvement phase, right? So your improvement phase in S1, policy in S1 would be max action of, or rather argument of Q1, let's take this Q1, Q2, Q2, okay, Q11, Q12, Q21, Q22, okay? So here you have Q11, comma Q12, okay? Which is the maximum value here? Q11 or Q12? Right? Right. So it is the second index, okay? And here say you define your action space as left comma right. So your action, your optimal policy in that case would be the second index thing in the action space, and that is right. Similarly, for pi of S2, you take argmax of Q21, comma Q22. In this case, which is a higher value? 1 or 2? Minus 1. 2 corresponds to right. So right. So now your policy is S1 take R, S2 take R. Got it? Clear? Sorry?
All of the second step start in Q.
Yes.
Policy improvement.
Policy improvement. Okay? Done? Again, what you can do is you can reiterate everything now. This entire thing, you reiterate. That would be policy iteration sweep 2 or iteration 2. You do that again and again and again and again. This will converge to an optimal value. This will converge to an optimal value, and finally the corresponding pi would be the optimal pi for that particular state and action, which in this case will be this one. Right? In the next state, when you do it, you will get a minus 1.9, minus 1 and 0 here. Similarly, you will get those values here, and you will get RR as the best action in that state. Yes?
If I get a value function, state value function, and be fixed,
Yes.
this not will be changed, right? I can't iterate here after I get a fixed value for the state value function.
No, you have to now, because how do you start now? The next action you will start with right and right. So in the next iteration, your VS2 would not be half, because now you're deterministically taking right. Your policy is also deterministic in the next state. This is your policy, right and right. So this entire thing will eliminate. You will have this, you will not have this, you will have only this, right? Then you will again evaluate your policy, again find the optimal, improve the policy. Then if it doesn't change, the actions doesn't change, the policy doesn't change, it means that the policy is converged to the optimal policy. Yes. Okay. I'll do one more iteration here. At this stage, what was our policy?
50%
Yes.
right?
We could either take right or left. Now, this was step 0. This is step 1. Step 1, we know that we are starting with right and right. Okay? So your value function of S3 will obviously be 0. Okay? Your S2 would now be, it is deterministic, right? So this summation will be 1. Your actions, you have only one action now. You get immediate reward plus gamma of V of
S1 or
S3, right? I mean, this is S3, right? Your policy tells you move right. So if you move right from S2, where do you end up in? S3. So that's why you need the value of future discounted value of VS3. Similarly, VS1, what is the ideal prescribed policy now in VS1?
gamma VS2.
Gamma VS2. Yes. You got me? Okay, yes. So VS2. Now you evaluate. You get some values here. You will get basically minus 1.9, minus 1, 0. Okay? This would be your V. This is your evaluation, step 2, or rather iteration 2. You again start here, right? You again evaluate the policies now.
So how many iterations can be fixed after that we can change the policy?
Okay. That is done till this converges. By convergence, I mean that this policy doesn't change. You get it? If the actions don't change, say if in this iteration we are doing it again. Okay? Now again, this time you plug in minus 1.9 here and minus 1 here. Minus 1.9 here, minus 1 here. Or yes, 0 here, okay? Then you do it, you will again get some values here, for which you take the maximum argument to see which action you should take. You will end up again getting R comma R. So if the policy doesn't change from the previous policy, it means that your policy is converged, right? In this step, you have 2. But if the problem gets more complicated, you will see, like in the next example, that you will have to do multiple iterations. Are we clear on this? Yes. This one now, after step 0, we do not consider it to be optimal because we want it to converge. So we want to make sure that there is no other policy better than this policy, right? So we do one more iteration. Cool, everyone? Yes. In the first step, yes, we check both. Why? In the first iteration. Why? Because we don't know what action we want to take. So we'll test it for both actions. However, in the second iteration, because your starting point is this now, you deterministically know, okay, you 100% with certainty know that you will take a right. So you will only evaluate it for the right action value functions, right? Yes.
So why do I calculate for the left and right again? Since I took right.
This one you have to, because the value function here changes. You're still considering, how will you improve otherwise? If you have only 2 actions and you deterministically, or you only consider right here, you're not even considering the other option. So what you're doing here is, okay, now given that I start with that policy and I take these steps now what will happen? That is what this is telling you, right? That's why you have to do for both or all possible actions here. Yes. Oh, okay, sorry.
So I think
Yes.
with this step we are just getting the corresponding action for this state values. And
With this step,
it reads the policy. With this step
Mhm.
we are just getting the corresponding values for this state value.
exactly. For whatever your evaluated value function is, you're getting this action value function for that value functions.
By which it will get the
Yes. Clear? Okay. Now this method was through policy iteration, okay? Assume the same problem you want to solve with value iteration now, okay? Implying you want to combine the evaluation and the iteration improvement part into one.
Can you please read just the last 2 lines all the way to the
Here.
these 2
This is value of state S1. for this policy. So you will have only one action, which would be the immediate reward for taking that action plus the discounted future reward of moving into the next deterministic state if you take this action, which is gamma of Vs2. And if you substitute it, you will finally get this value. So your V would be minus 1.9 because you're further away. S1 is the furthest from the goal, that's why it has the lowest value. This one, Vs2 is the closest to the goal, that's why it has minus 1. Vs3, which is the goal itself, is 0 basically. Right? Okay. Now in this step, like I said, you will combine the two. How? See, your Vs3, which is 0. Okay? Your Vs2 would be, now you take the max value of,
Sorry, what step are we in now?
now this is an alternate method, value iteration.
Okay.
Value iteration. That was policy iteration. This side, what we did on this side of the blackboard was policy evaluation. That side was policy improvement. From here on, it was the second iteration. That is done. We got the ideal policy with policy iteration. It says that the ideal policy or the optimal policy is simply right, comma, right. Right? In the two states that we have. Here, so now you are in S1, right? So what are the possible actions that you can take in S1? Yes, so it would be minus 1 plus 0.9 times Vs1 for left plus, oh no, comma, minus 1 plus 0.9 times Vs2. This is for Vs1, Vs3. Similarly, for Vs1, you would have max of minus 1 plus 0.9 times Vs1, comma, minus 1 plus 0.9 times Vs2. Right?
We don't use the transition probability because these are skewed, right?
Yes, and also we are considering all the possible actions here.
I mean, we didn't use 0.5.
We are taking two actions here.
Yes, okay, but we don't put the 0.5 as in the value.
No, because you are already considering all actions separately here.
Okay.
So the function, the equation itself doesn't have pi?
You mean the summation over pi?
No, just pi, like the max of the pi times.
No. Because here you are considering all possible actions. Say if it were 6, you would have 6 arguments here in this max function.
Can you write the general equation here?
This would be the general form. Yes.
If it wasn't 50%, it would be the same. I mean, if the transition probability.
Yeah, that's why if you had 6 arguments here, if you had 6 possible actions, you would have 6 arguments in the max function, and then you would take the maximum numerical value.
But I mean, if they are not equally probable.
Oh, you mean the transition probability? Yes, then you would have to multiply it by the transition probability. Yes. Sorry? This is the action probability included here. Here, the action probability is basically equally divided. But your transition probability might vary. Okay? In this case, it is 1, yes. But then they were asking like if it is not 1.
It would be embedded in this equation. The Q.
Yes, so yeah, okay, yeah. Q will have the probability function here. So yes, in that sense, yes, you will have probability there already within this, right? Okay, you do this, right? You will get a value here. Okay, now again, you start with V of 0, 0, 0, which is your initial V, okay? Your random guess basically. You plug in that values here, you get some value, right? You would get a initial first value. So you will get V1 of S3, V1 of S2, V1 of S1. Cool? Right? With this, you extract the, so okay, so you already know here, right? You know which argument is your maximum value. So your optimal policy would be,
I'm at 1, so
you're at
two arguments are V of S1 and the other is V of
S2. V of S2. Because you can move left, right. Then we extract the policy. Okay. VS1, VS2. Yes, so we'll see, okay, which is giving us the maximum value of Q, argument 1 or argument 2, left or right basically. Then from that you deduce the policy. Also your value function numerically will also be similar to this one, that is 1.9 comma minus 1 comma 0. So no matter what method you follow, policy iteration or value iteration, your converged optimal value will numerically be always equal. Yes.
This here is one iteration, right?
Yes, up until this point, I didn't do the calculations. So if you plug in 0, 0 here, you will get one value. You start with that value next time. Again with the next value you again start. You keep on doing this till your value function doesn't change. Once it is stable or within a certain tolerance, then you know that it has converged. Based on that you will extract the policy, right? So here you don't have policy improvement every iteration, right? Okay, clear everyone up until this point? Yes.
VS1 equal
Max of the left action you can take and the right action you can take. Left action would be staying in S1, so this would be minus 1 plus discounted value function of S1, right? Clear?
I think that's V1. What is 1 all the way down?
V1 S3.
What is 1? V1.
Value function after the first iteration. This is V0. We assume it is 0, 0, 0. First iteration V1, second V2, and it goes on till we get V star. When we get V star, we take pi star from it. Right? Cool, everyone? So clear this problem. Okay? Yes.
Can I start by it? I can get the max, and from that I can get what is the best action to take. Here I know the right is the best from the max.
Yes.
Can I start by it?
Start by what you mean? Start by taking right?
Yes.
That would be your policy iteration method. Here you don't care about the policy because you are considering all actions. You do not need to have an initial policy. In value iteration, because you consider all actions, you're considering right, you're considering left. You get the point? Whereas in policy iteration, you needed to have an initial policy, a random policy. There you could start with right, and then you would simply end up getting right in after the first iteration. Second iteration you do, it would again give you right and right, which would imply that your ideal policy or your optimal policy, rather, I keep using ideal, I don't know why. Optimal policy is right and right. Cool? Got it? Okay. So now your problem is this one, okay, the one that we talked about earlier as well. Start at top left, reach bottom right with a wall in between which doesn't do anything. So basically it prevents you from coming into that state. So you cannot go into that state. However, you have a fire pit here where if you fall, you would end up, you would simply end the game, okay. So you have two terminal states here, okay. What are terminal states again? Yes, right? The states at which the episode ends. Okay? Clear, everyone? Okay. So, these are just some initial values. We will initialize it. Okay? Okay. Oh, you want further zoomed? Is this good? Okay. Okay. Okay, so here we define the parameters first. Your gamma, that is your discount factor, is 0.9, step cost minus 0.1, and then total number of rows and column, and then you give the values here to the cells, like which cell are wall, pit, and goal. Okay. Also, you have a certain what? If outside the states are invalid, outside the grid, it's an invalid word. So you stay in that same state if you take an action in the edge, in the border states, which would result in you ending up outside the grid world, right? So those are invalid actions. Okay. Now here we could have each state you could have combinations, right? You could. This is basically just a way of doing it here in MATLAB. Like the The second set of vectors you see -1 +1 0 0 0 0 +1 -1, that's combination basically, okay? So what it means is you have a grid world, right? You have a grid world, right? In each box you can move up and move sideways. So there are two possible combinations that you can move. So this will sum up that thing. You can either move, and since you cannot move diagonally, you will see here that combinations are, if the column movement is 0, you have row movement. If row movement is 0, you have column movement. Okay? This is just a way of doing it in MATLAB, okay? Okay, so you initialize it, you will get something like this. This is your grid world. You can see that, right? Or is it small? Okay. Now this is just flattening, because you have a 2D world which we will flatten it to 1D. Okay, so this will simply tell you, okay, yeah, this is done. Okay, now coming to the, just for calculations, because it's easier to do in MATLAB that way. So you assume that you stack everything in one line and then you move states, and then you again deconstruct it to make a grid world to get the optimal policy. Okay. I will obviously upload this code which you can go through. Okay, so yes, here it will give you this preview, okay? This is action basically. If you up action, down, back, or right, left, or down, up, down, okay? If you are in state 3, 3, that is, this is 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 2, 4 is fire, 2, 2 is wall, 3, 4 is goal. So now this is just to give you a preview of how the reward function works, or how the transition function works. Is if you are in 3, 3, you go up, you will go to 2, 3. No, you will not go to fire. From 3, 3, if you go up, you will go in 2, 3. If you take a left, you will go to 3, 2. If you go down, you will stay in 3, 3. If you take a right, you will go to the goal. That's why you will see rewards here. For all actions it is -1 except for going to the goal. Okay? Here it is +1 for going to the goal. Right? Okay. So now, okay, we do the value iteration. Okay. Initially we have everything zeros. We initialize the grid world with zeros, except for, yeah, okay, even the pit and goal are 0. Okay. We do the first iteration, first sweep. Okay. You get this values. Okay. You're doing value iteration here, okay? So it doesn't have separate policy evaluation and policy improvement steps. Everything is done in one step, right? Then you calculate the Q functions for that to obtain the corresponding policy, right? Here your policy, okay. This is basically just hand calculation of doing for every grid. For example, I have shown only 2 states here for 3, 3 and 2, 3. Okay, you can do it for all the states exactly like that. Okay, let me tell you again. You're here in 3, 3 for this example. You're here in 3, 3. Okay, before getting this value, I mean. Okay, how do you obtain these values? This calculation shows you that. Okay, you're in 3, 3. You take up, you get a reward. Your Q value is -0.1. For up in S3, 3. For down in 3, 3, you have I wrote it wrong. T33 plus 1.8. Okay, yeah, this I made a mistake. Okay, so you will get again a value here. For down, you will again get the same value. For left, you will get the same value. For right, however, you will get the best value. Okay, you do that, you fill in here. So that's why the best value here is 1, because you go to the goal, right? Similarly, you do that for all the states. you will fill in the grid world with the value function after the first sweep. Okay? Then you do second iteration. Now your value function again will update. You see your value function changed now. It's not the same, implying that there is still need for a third iteration or a third sweep because it did not converge yet. Okay? You get some values there. You do the third sweep now. Okay? Again you get some values. You basically repeat it multiple times. You do multiple sweeps. Okay? For every sweep you will see how the value function is changing. This is how the value function is changing here. You see? You can see this, right? This is value function after the sixth sweep. You do that again and again and again, and finally, based on your optimal policy, this is your optimal policy. It says if you are in state 1, go down, right, 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 and right. Okay. Here, how many steps are you taking? 1, 2, 3, 4, 5. Okay. However, if you come from above, 1, 2, 3, 4, 5, you would still reach in 5. So you have two optimal policies here, right? Which depends on how you start from here. If you move right, you have to go right and then down and down and right. Here also, if you start going down, you go down till you reach the last row and then you take a right till the end, right? So why did we choose this here, downward action here?
Because it's away from the fire?
No, basically the value will be same for both the actions. It will not change. It's just basically a tiebreaker rule. So if you have two possible actions in one state which are optimal, you can choose any of the actions. Okay? You can choose any of the actions which would result in that particular motion. Okay? So if you have two optimal actions, and you might have two optimal actions, okay, in that state, you can choose any action. It doesn't matter, because your final value function would be optimal. Okay? Irrespective of the action you take, if the action is optimal in that state. Okay? So you see, remember that grid world. I'll take a screenshot and keep it. So this policy you got for value iteration. Okay? Where did that go? Yeah, okay, we have it here. Okay. Now if we do the same thing with policy iteration, initially here you're starting with a policy that says, what does your initial policy say? Go up in all states. Okay? So that is your policy. Here you don't have to sum it over the actions. Why? Because you are defining a policy which says always go up. Okay? You do always go up. Then you evaluate your value function for that policy. Okay? Because it's a complicated one, you cannot do it, or rather you could, but you still don't want to do it by hand. Sorry, by analytical method, you try the numerical method. For that you need to have some initial values, which in this case is 0. Then you do the first sweep. Okay? And you keep repeating it exactly like how we did for this case, for the simpler case. You remember how we did? Initial random policy, we evaluated the value function. Based on that value function, we computed the Q function, from which we derived or improved the previous policy that we had. And then with that improved policy, now as the starting point for the next iteration, we again compute the same things. Like we repeat the cycle, compute the value functions, then again get the Q value functions, from which we will get the optimal policy. And when we get the improved policy, and again when we get this improved policy, we repeat the cycle.
But here the probability of action, it will be 1 over 4, right?
Where, sorry, we have?
Probability of action.
But
it will be 1 over 4.
No, that's why we are defining the policy here, that the initial policy says that you're deterministically going up in every state. Right? That was the case when you had a stochastic policy. Here, you're assuming that you have a deterministic policy. So whenever you have a deterministic policy or a deterministic transition, these two summations collapse. Basically, they become 1. Right? If you have a deterministic policy or deterministic transition, your summations would collapse to 1. Cool? Got it? Sure? Okay, where were we? Yes, okay. So now again, you start with 0, 0. You do a first iteration, you get some values. You repeat that many times. You see you're doing that again. Okay, here you're computing delta. Delta is basically the difference in the change in value function for every state, okay? Notice you have how many? You have 12 states, right? 9 active states. 3 don't have any value function. You have 9 states for which you should have a value function, right? But the computed delta here is only 1, right? So for which state are we doing it? We are doing it for the state that has the maximum change. So this would simply mean that if your maximum change is this much from the previous iteration, all others will obviously be less than that. So we just want to make sure that the maximum change is less than our tolerance. Okay, you can define the tolerance whatever you want. In this case, I have 10 to the power minus 8, which is very small, right? Yes.
Sorry, what is tolerance? I mean, tolerance for what? For change?
Yes, tolerance here, because it was a simple environment, when you did multiple sweeps or multiple iterations, the value function changed, but after 2 or 3 sweeps, it converged. It didn't change anything.
You mean the tolerance of change to?
Yes, tolerance of change. Yes, that is how you define the convergence basically. Okay, based on the change. Okay, here it was simple case, so that's why it changed in 2, 3 iterations and it stabilized. It didn't change at all. The change was 0 between any two, between the next iteration and the current iteration, right? However, this being a more complicated problem, the change is more, right? It happens more and it happens for a longer period of time. That's why you have more sweeps. You have 154 sweeps to be exact here. So you have to do 154 iterations before the value functions converge. Okay, again your value function converges. You do that. Okay, yeah. Again, remember this are 2 steps, right? Policy evaluation and iteration. So you do that. Now second iteration for the same thing. You keep doing it. You repeat all that. Iteration 5, iteration 6, till your final value function. So your final, here is your final value function. Oh, sorry, your final policy based on your policy iteration, right? Just let me show you this image. Okay. The one above is your policy iteration based optimal policy. The one below here, value iteration based optimal policy. You see they're the same. Oh, sorry, I took a wrong image. Oh yeah, sorry, I took the wrong screenshot. Okay, anyways, I have the comparison here. Yeah, okay, here I have the comparison. So here, your policy based on value iteration, your policy based on your value iteration. They are the same, you see? Implying that no matter what method you choose, you will end up in the optimal policy. It is just that how fast or how efficient that processing is, that computation is. Yes?
Can you just go to the value table?
Value table, I will go through it.
Value function of the file, why it is always 0?
Value function of?
Of the state, the file, state.
Because it's the terminal state.
So,
What did we
define here or?
What did we define? That the terminal states has a value function, has the reward of 0. But the transition itself will give you some effects or some reward, which in this case was -1 if you move from here to here, +1 if you move from here to here, right? So that's why since these are terminal states, their value function is 0, because once you go there, it's over. So what is the value function again? It is current reward plus future discounted reward. So there is no future discounted reward there. That's why it's 0. Right? Clear, everyone? Yes.
For the previous example, this example,
Right.
between deterministic policy, the deterministic policy, you mean that we have an initial value for the policy?
Yes.
But here we don't.
Yes. Yes. Here we don't. Because it was simpler problem, we could consider that situation.
I initialize this?
Yeah, even if you initialize it, say you initialize it left and left, then you compute it only for left and left, you get some value function here. When you do this, you will get some action value functions, which would then result in an improved policy. You would get some improved policy, which will then be a starting point for the next iteration of value function computation, which you will repeat again. right? Clear, everyone? I hope this cleared your issue with the value function calculation and computation. Now it's clear, everything, every step of it, right? Now all we will be doing is, in the remaining lecture, is just keep complicating this MDPs basically, okay? Now you have deterministic action, deterministic policy, and discrete action space, discrete state space. As we move forward, it would become continuous. It would become stochastic. This keeps on getting more complicated, for which you will be needing more complicated ways of solving, right? That's all we'll be learning. So from now on, everything would be solution of these equations to obtain the optimal policy through different algorithms, okay? RL theory is this much. From next class onwards, you will have RL algorithms.